morning, all of you. Today I'm going to make an audio recording for visually impaired student of organic chemistry book of S. Kiran Kavya Modern Book. Name of the chapter is Electrochemistry. Electrical transport. A substance which allows an electric current to pass through it is called a conductor, while the substance which does not allow electric current to flow through it is called an insulator or non-conductor. The conductors are of two types, electronic conductors and electrolytic conductors. Electronic conductors. Electronic conductors are the substances which do not undergo any chemical change as the electric current flow through them. For example, metal, graphite, and some minerals. The conduction through electronic conductors is due to the flow of electrons in them. Electrolytic conductors. The substance which conduct electricity in their molten state or through their aqueous solution and which are decomposed by the passage of electric current. For example, aqueous solution of acid, base and salt, modern salt. In this type of conductor, the electric current is due to the movement of by ions. This type of conduction is referred to as electrolytic conduction. Electrolytes are further classified as strong electrolytes and weak electrolytes. Strong electrolytes are substances which are almost completely dissociate into ions in their aqueous solution or in molten state. For example, strong acid like HCl, H2SO4, etc., strong bases like NaOH, KOH, etc., and salt like NaCl, NH4Cl, etc. Weak electrolytes are substances which dissociate in aqueous solution to a smaller extent. In other words, they have low degree of dissociation. For example, weak acid like HCl, H3PO4, CH3C double bond OH, and weak bases like NH4OH, etc. Since they have low degree of dissociation, so they conduct electricity to a small extent. Non-electrolytes. Substances like urea, glucose, etc., which do not conduct electricity in the molten state or through their aqueous solutions are called non-electrolytes. Ethyl alcohol, sugar are also examples of non-electrolytes. It is interesting to note that whereas the electrical conduction of electronic conductors decrease with increase of temperature, but in case of electrolytic conductors, it increase with temperature. Factor affecting electrolytic conduction. In aqueous solution or molten state, the electrolytes split up into ions. The free movement of ions is responsible for the conduction of electricity. The electrical conductivity of solution should therefore be related to the number of ions present in the solution. Some of the factors on which electrical conductivity of the solution of electrolytes depends are: first, the interionic attraction. These are the attractive interaction between the ions formed by the electrolytes in the solution and are known as solute-solute interaction. Larger the interionic attraction, lesser is the freedom of movement of ions and smaller will be the electrical conductivity. Second, the solvation of ions. These are the attractive interaction between the ions of the electrolyte and the molecule of solvent and are known as solute-solvent interaction. Larger the solute-solvent interaction, larger will be the solvation, lesser will be the movement of ions, and hence lower will be the electrical conductivity. Third, viscosity of the solvent. This factor depends upon the attractive interaction between the solvent molecules, which is referred to as solvent-solvent interaction. Larger the solvent interaction, larger will be the viscosity and more will be the hindrance to the movement of ions. Hence, lower will be the electrical conductivity. The above factor decrease with increase in temperature. As a result, the kinetic energy of the ions increase or increase in temperature. This results in the increase of electrical conductance of electrolytic solution with rise in temperature. This is in contrast to the behavior of electronic conductors in which the conductance decrease with increase in temperature. Alternatively, we can say that conductivity of electrolytic solution depend upon the following factors. First, nature of electrolyte. The conductance of an electrolyte depend upon the number of ions present in the solution. The number of ions produced by an electrolyte depend upon its nature. The strong electrolyte dissociate almost completely into the ions in solution and therefore their solution have high conductance, whereas weak electrolyte dissociate to a small extent, hence their solution have low conductance. Second, nature of the solvent. Electrolytes ionize to greater extent in polar solvents. Therefore, greater the polarity of the solvent, larger is the ionization and hence greater is the conductance. Third, concentration of the solution. On increasing the concentration, the electrolyte conductance decrease in the case of both weak as well as strong electrolyte. Because with increase in concentration in case of weak electrolyte, the ionization decrease and in case of strong electrolyte, the interionic attraction increases. Fourth, temperature. The conductivity of an electrolyte depend upon the temperature. With increase in temperature, the conductivity of the electrolyte increase due to the increase in dissociation. The difference between metallic conductors or and electrolytic conductors are given in table 1. Metallic conductors, electrolytic conductors. First, these remains unchanged as the current flow through them, whereas electrolytic conductors undergo a chemical change by the passage of electric current. In case of metallic conductor, flow of electricity is due to the presence of mobile valence electron, so it involves no transfer of matter. Whereas in case of electrolytic conductors, conduction is carried by ions, hence it involves transfer of matter as ions. Third, metallic conductance involves no change in the properties of the conductor, whereas in case of electrolytic conductor, electrolytic conduction involves the decomposition of the electrolyte as the result of chemical reaction. In case of metallic conductor, the resistance is due to the vibration of metal ions about their mean position which hinder the flow of electric current. Whereas in the electrolytic conductors, the resistance of an electrolyte solution is due to the factor like intraionic attraction, viscosity of the solvent, etc. Fifth, metallic conductance decrease with increase in temperature. This is because on increasing temperature, the frequency of vibrating kernels increases. Consequently, the resistance of metallic conductors increase, which creates hindrance to the flow of electron and its conductance decrease. Whereas in case of electrolytic conductors, electrolytic conduction increase with temperature. This is due to the increase in dissociation of electrolyte and decrease in interionic attraction with increase in temperature. Sixth, the conductivity of metal is generally high, whereas in case of electrolytic conductors, the conductivity of electrolytic solution is generally low. Electrical resistance and conductance. Electrolyte solution conduct electricity through them by the movement of ion towards the electrodes. Like metallic conductors, electrolytic conductors also offer resistance to the flow of electricity. Hence, electrolytes also obey Ohm's law. According to Ohm's law, the current flowing through a metallic conductor is directly proportional to potential difference across it. It means I is directly proportional to V, or I is equals to V by R, or V is equals to IR, where R is the constant of proportionality and is known as resistance of the conductor. It is expressed in ohms and is represented as ohm. Current is generally measured in amperes and potential difference V is measured in volt. According to Ohm law, R bracket ohms is equals to V volts divided by I ampere. Unit of resistance. The unit of resistance is ohm. In term of SI base unit, ohm is equals to kilogram meter square divided by S cube A square. This unit is obtained as ohm is equals to V by A is equals to work per unit charge divided by area is equals to work by charge into 1 by area. Is equals to force into length divided by A into S into 1 by A is equals to mass into acceleration into length divided by A square into S is equals to kilogram into meter per second square into m divided by a square s is equals to kilogram meter square divided by s cube a square. The interesting feature of electrolytic solution is not the resistance they offer to flow of electricity but that they allow it to flow. Consequently, the important property in electrochemistry is conductance. Thus, conductance is the measure of ease with which current flow through a conductor. From Ohm's law, it follows that a substance which offers lesser resistance will allow more electricity to pass through it. Thus, conductance is the reciprocal of resistance. It is represented by C. C is equals to 1 by R. Unit of conductance are reciprocal ohm. It means ohm inverse or mho. Ohm is abbreviated as ohm. So ohm inverse may be written as ohm inverse. Electrical conductance is also expressed in Siemens as 1 Siemens is equals to 1 ohm inverse, named after noted electrical engineer Sir William Siemens. Specific conductance, equivalent conductance, and molar conductance. First is specific conductance. The resistance R of a conductor is directly proportional to its length L and inversely proportional to its area of cross section A. It means R is directly proportional to L by A or R is equals to rho into L by A, where rho is a constant of proportionality and is known as specific resistance or resistivity. Value of rho depend upon the material of conductor. From equation first we have rho is equals to R into A by L is equals to ohm centimeter square divided by centimeter is equals to ohm centimeter ohm or ohm centimeter. L is equals to 1 centimeter and A is equals to 1 square centimeter, then rho is equals to R. Thus, the specific resistance or resistivity rho is defined as the resistance of a conductor of 1 centimeter length and having area of cross section equals to 1 centimeter square. In other words, resistivity or specific resistance is the resistance between opposite faces of 1 centimeter cube of conductor. In SI unit, it is defined as resistance when the conductor is 1 meter long and its area of cross section is 1 meter square. It means resistance of 1 meter cube of the conductor. Units of resistivity are ohm centimeter. The SI unit are ohm meter. 1 ohm meter is equals to 100 ohm centimeter or 1 ohm centimeter is equals to 0.01 ohm meter. The reciprocal of specific resistance rho is known as specific conductance. It is denoted by symbol K kappa or K. Thus K is equals to 1 by rho. K is equals to 1 by R into L by A or K is equals to C into L by A. If L is equals to 1 centimeter and A is equals to 1 square centimeter, then K is equals to C. Hence, specific conductance is defined as the conductance of solution of 1 centimeter length and having 1 square centimeter as the area of cross section. In other words, specific conductance is the conductance of 1 centimeter cube of a solution of an electrolyte. The unit of specific conductance are derived as follow. K is equals to 1 by A into L by R is equals to 1 by ohm into centimeter divided by centimeter square is equals to ohm inverse centimeter inverse or Siemens centimeter inverse. In SI unit, the area of cross section is expressed in meter square and length is expressed in meter. Then the unit of specific conductance are Siemens meter inverse or ohm inverse meter inverse. 1 ohm inverse centimeter inverse is equals to 100 ohm inverse meter inverse or 1 Siemens centimeter inverse is equals to 100 Siemens meter inverse. Equivalent conductance. The current in an electrolyte is carried by ions. A particular volume of solution may contain more or less ions depending upon its concentration. Therefore, the conductance of the solution varies with concentration. So, for comparing the conductance of different solution, it is required that they should have same value and must furnish amount of ions carrying some total charge. This can be achieved by taking equal volumes of solution containing their respective gram equivalent masses. The conductance of each such solution is called gram equivalent conductance. Equivalent conductance may be defined as the conductance of solution containing 1 gram equivalent of electrolyte dissolved in V centimeter cube of solution such that the whole of solution is placed between two electrodes 1 centimeter apart. It is denoted by symbol lambda equivalent. Equivalent conductance represent the conducting power of one electrovalent of the given electrolyte at the given dilution or concentration and temperature. Relation between specific conductance and equivalent conductance. The equivalent conductance lambda is equals to the product of specific conductance and the volume V in centimeter cube, which contains 1 gram equivalent the electrolyte. Thus, lambda equivalent is equals to K into V. This relationship is deduced as follows. Consider a rectangular vessel with its opposite wall acting as electrodes placed at distance of 1 centimeter. Suppose 1 centimeter cube of the solution containing 1 gram equivalent of electrolyte is placed in this vessel and its conductance is noted. The conductance of the solution represents specific conductance K. Further, as 1 centimeter cube of the solution contains 1 gram equivalent of electrolyte, hence its conductance will be its e- equivalent conductance lambda equivalent. Thus, for 1 centimeter cube of solution containing 1 gram equivalent of electrolyte, the equivalent conductance lambda equivalent is equals to its specific conductance K. Now consider 4 centimeter cube of solution containing 1 gram equivalent of electrolyte placed between two electrodes 1 centimeter apart. The solution can be considered as consisting of 4 cubes each of volume 1 centimeter cube figure 2. The conductance of each of these cubes is equals to specific conductance K. Thus the total conductance of the solution will be 4 into K. Similarly, VCC of the solution will be V cubes and total conductance will be K into V. In general, for a solution containing 1 gram equivalent of electrolyte in V centimeter cube, we have equivalent conductance is equals to specific conductance into V. Lambda equivalent is equals to K into V. Equation first. In term of concentration, if a solution contains C gram equivalent of electrolyte in 100,000 cc of the solution, then the volume of the solution containing 1 gram equivalent will be 1000 divided by C. Thus, expression first can be written as lambda equivalent is equals to K into 1000 divided by C equivalent is equals to K into 1000 divided by normality. Unit of equivalent conductance. The unit of equivalent conductance may be derived as follows. Lambda equivalent is equals to K into V. We know K is equals to 1 by R into L by A. So 1 by R into L by A into V. We get the unit is Siemens centimeter square equivalent inverse, or the SI units are Siemens meter square equivalent inverse. Both the type of unit are related as 1 Siemens centimeter square equivalent inverse is equals to 10 to power 4 Siemens centimeter square equivalent inverse, or 1 Siemens centimeter square equivalent inverse is equals to 10 to power minus 4 Siemens meter equivalent inverse. Molar conductance. Molar conductance of a solution at dilution V is defined as the conductance of all the ion produced from 1 mole of the electrolyte dissolved in VCC of solution such that the whole of solution is placed between two parallel electrodes 1 centimeter apart. It is denoted by lambda m. Relationship between molar conductance and specific conductance. Molar conductance of solution is obtained by multiplying the specific conductance by the volume V in Cc, which contain 1 mole of the electrolyte. Thus, lambda m is equals to K into V, where V is the volume of solution in centimeter cube containing 1 gram mole of the electrolyte. If a solution contains C moles of electrolyte in 1000 cc of the solution, then the volume of the solution containing 1 mole will be 1000 by C. Thus, above equation may be written as lambda m is equals to K into V in centimeter cube containing 1 mole of electrolyte, or lambda m is equals to K into 1000 divided by C is equals to K into 1000 by molarity. Here K is the specific conductance and C is the molar concentration. It means mole liter inverse or mole decimeter inverse. Unit of molar conductance. Lambda m is equals to K into 1000 divided by C. The unit of K are ohm inverse, centimeter inverse, and units of lambda m are derived as lambda m is equals to ohm inverse, centimeter inverse into centimeter cube divided by mole liter inverse is equals to ohm inverse centimeter square mole inverse or ohm inverse centimeter square mole inverse. According to SI unit, in SI unit when K is in Siemens meter inverse and molarity is in mole meter inverse cube, then lambda m has unit Siemens meter square mole inverse. Both the type of units are related to each other as 1 Siemens meter square mole inverse is equals to 10 to power 4 Siemens meter square mole inverse. 1 Siemens centimeter square mole inverse is equals to 10 to power minus 4 Siemens meter square mole inverse. Measurement of conductance, specific conductance, equivalent conductance, and molar conductance. First, measurement of conductance. The conductance of solution is reciprocal of resistance, therefore, it can be determined by measurement of resistance of the solution. The resistance of a solution can be measured with the help of Wheatstone bridge method. The principle of Wheatstone bridge method, figure 3, is as follows. It consists of four resistance R1, R2, R3, and R4. Resistance R1 is a variable resistance and R2 is an unknown resistance of electrolyte solution. When the current flows through the circuit, the resistance R1, R2, and R3 are so adjusted that the null point is obtained. The null point is indicated by zero deflection in the galvanometer G. At null point, R1 divided by R2 is equals to R3 by R4. The resistance R1, R3 and R4 are known and the value of R2 can be calculated. To determine the resistance of electrolyte solution, one arm of Wheatstone bridge is attached to the conductivity cell containing the solution. The conductivity cell figure 4 is made of Pyrex glass and is fitted with platinum electrode. These are coated black with finely divided platinum figure 4. However, for measuring the resistance of electrolyte, the solution direct current DC cannot be used because it causes electrolysis of the solution. As a result, the concentration of the electrolyte near the electrodes change and this result in the change in the resistance of the solution. These effects are called polarization effect. To overcome this problem, following modification are done in the usual Wheatstone bridge. First is the bridge is connected to a source of alternative current of frequency 550 to 5000 cycle per second is employed. Second, a headphone is used in place of a galvanometer because with alternating current, ordinary galvanometer fails to detect the null point. Third, the cell is placed in the thermostat to keep the temperature constant. This is to avoid change in the conductance with temperature. Fourth, electrolytes are coated with platinum black. The arrangement used for measurement of resistance is shown in the figure 5. A sliding conduct contact J moves over a stretched wire AB. R is the resistance spoke and conductance cells containing electrolyte solution is placed in the circuit. There is a source of alternating current. A resistance R is introduced in the resistance box. The sliding current J is moved along the wire AB until the sound in the earphone is minimum says to point H. If X is the resistance of the electrolyte solution, then according to Wheatstone bridge principle, we have resistance R divided by resistance X is equals to resistance AH divided by resistance BH is equals to length AH divided by length BH. Resistance X is equals to resistance R into length AH divided by length BH. From the value of R and the length AH and BH obtained from null point, we can calculate the resistance X of the electrolyte solution can be calculated. The resistance of the electrolyte solution is converted to conductance using the following equation. Conductance C is equals to 1 by x is equals to 1 by r into length BH divided by length AH. Calculation of specific conductance. Specific conductance K of electrolyte solution can be calculated as follows. K is equals to C into L by A first equation, where C is the conductance of the solution. Here L is the distance of separation of two electrode and A is the area of cross section of electrode. The quantity L by A is called cell constant. The cell constant is expressed in the unit centimeter inverse. The equation first can be written as specific conductance K is equals to conductance into cell constant. Once the specific conductance is determined, the equivalent conductance lambda equivalent and the molar conductance lambda m of the solution can be calculated. We have the expression specific conductance K is equals to 1 by R into L by A second, or specific conductance is equals to observed conductance into cell constant. Third, determination of cell constant. The cell constant L by A can be determined by measuring the distance L between the electrode of the cell and their area of cross section A. Actual measurement of these dimensions for a given cell is difficult. Therefore, an indirect method is used to determine the value of cell constant of a cell. The cell constant is generally not calculated from the value of L and A because these are difficult to measure for a cell. However, it is usually determined accurately by measuring the conductance of a standard solution of KCl, whose conductivity is known at different concentration and temperature. The conductivities of different KCl solution at 298 Kelvin are given in table 2. Once the cell constant is known, the specific conductivity of the given solution can be calculated from the observed conductance of the solution. For example, for 0.1 mole KCl solution at 298 Kelvin, conductivity is 0.0129 Siemens centimeter inverse. Suppose the conductance of this solution is in the given cell is measured to be x. Then cell constant is equals to conductivity divided by conductance is equals to 0.0129 divided by x. Fourth, calculation of equivalent conductance lambda equivalent. Equivalent conductance and specific conductance are related as lambda equivalent is equals to K into 1000 divided by C equivalent, where C equivalent is the concentration in gram equivalent per liter. It means the normality of the solution. Thus, knowing specific conductance and normality of the solution, we calculate equivalent conductance of the solution. Fifth, calculation of molar conductance lambda m. Molar conductance lambda m and specific conductance are related as lambda m is equals to K into 1000 divided by Cm, where Cm is the concentration in moles per liter, it means the molarity. Thus, knowing the value of molarity and specific conductance, we can calculate molar conductance of the solution. Unit of common terms used in the conductance are summed up below. Sixth, conductivity water. For accurate conductance measurement, the solution are prepared in extra pure water which is free from dissolved impurities. The extra pure water have very small conductance. Such extra pure water is called conductivity water. The specific conductance of this water is as low as 4.3 into 10 to the power minus 8 Siemens centimeter inverse. For practical purposes, conductivity water can be prepared by distilling ordinary water containing a small quantity of potassium permanganate, only a few crystals, and sodium hydroxide 0.6 gram in 2 liter, twice in Pyrex glass distilled apparatus. Title first. Electrolyte is a substance and dissociate in solution to produce ion. It conducts electricity in dissolved or molten state. Ohm's law. V by R is equals to V by I is equals to R. Specific conductance K is the conductance of 1 centimeter cube of a conductor. Its units are ohm inverse, centimeter inverse, or Siemens centimeter inverse. Equivalent conductance lambda equivalence is the conductance of solution containing 1 gram equivalent of electrolyte placed between two parallel electrodes placed 1 centimeter apart. Lambda equivalence is equals to 1000 into K, divided by n, where n is the normality of the solution. Molar conductance. Molar conductance is the conductance of solution containing 1 mole of electrolyte placed between two parallel electrodes placed 1 centimeter apart. Lambda m is equals to 1000 into K divided by m, where m is the molarity of the solution. Conductivity is equals to cell constant divided by resistance is equals to cell constant into conductance. Conductivity water. In conductance measurement, the solution is made in conductivity water. It is very pure water which has no conductance due to dissolved impurities. The conductance of such a water is of order 4.3 into 10 to power minus 8 ohm. Unit of some properties. Resistance ohm. Resistivity ohm centimeter. Cell constant centimeter inverse. Conductance ohm inverse or Siemens. Conductivity or specific conductance ohm inverse centimeter inverse. Molar conductivity ohm inverse centimeter square mole inverse. Equivalent conductivity lambda equivalent is equals to ohm inverse centimeter square equivalent inverse. Variation of conductance, specific conductance, equivalent and molar conductance with dilution. Generally, the electrolytic conduction decrease with increase in concentration or increase with increase in dilution. This is because the conductance is due to the presence of ion in the solution. The greater the number of ions, the greater is the conductance. With dilution, more ions are produced in solution, so conductance also increase on dilution. The specific conductance is the conductance of 1 centimeter cube of the solution. On dilution, the specific conductance decrease because the concentration of ions per centimeter cube decrease and therefore the specific conductivity decrease. On the other hand, the molar conductivity and equivalent conductivity increase on dilution. This is because the molar conductance and equivalent conductance are the product of specific conductance K and the volume V of the solution containing 1 mole or 1 gram equivalent of the electrolyte. It means lambda is equals to K into V. On dilution, the specific conductance decrease, but the increase in volume is much more than decrease in specific conductance K. As a result, molar conductance and equivalent conductance increase with dilution. Variation of molar conductance with dilution for strong and weak electrolytes. The variation of molar conductance on dilution for strong and weak electrolyte can be studied by plotting lambda m values against concentration in root inverse. The variation of lambda m with concentration is discussed below. First, for strong electrolyte. The molar conductance of strong electrolytes in dilute solution varies with concentration according to d by Huckel-Onsager equation as follows. Lambda m is equals to lambda m infinity minus b root c, where lambda m is the molar conductance and concentration C, and lambda m infinity is the molar concentration at infinite dilution and is called limiting molar conductance. Here B is constant which depend upon the type of electrolyte, nature of solvent and temperature. It is found that for strong electrolyte, example KCl, the d by Huckel-Onsager equation holds good at low concentration. As a result, the variation of lambda m is linear at low concentration, but it does not remain linear for higher concentration. The curve for strong electrolyte shows that there is a small increase in molar conductance with dilution. This is explained as follows. Strong electrolytes are comparatively dissociate at all concentration. Thus, the number of current carrying species it means the ion remain constant on dilution. Hence, the increase in molar conductance is not due to increase in number of ion. This is due to the fact that at higher concentration, the interionic attraction, the force of attraction between the positively charged ion are appreciable. This retards the motion of ions. Therefore, molar conductance falls with increase in concentration. On the other hand, with decrease in concentration, the ions are far apart and force of attraction between them decrease, due to which the molar conductance increase with dilution. As the solution becomes more and more dilute, the molar conductance increase till it reaches a maximum limiting value. This value is known as molar conductance at infinite dilution and denoted as lambda m infinity or lambda m naught. The value of lambda m naught can be obtained by extrapolating the curve to the value of root c is equals to 0. Second, for weak electrolyte. The weak electrolyte are dissociated to a lesser extent as compared to strong electrolyte. Hence, the molar conductance of weak electrolyte is much less than that of strong electrolyte at same concentration. Figure 7 shows that molar conductance of acetic acid weak electrolyte is lesser than that of KCl strong electrolyte. At the same concentration, the curve for a weak electrolyte there is a large increase in molar conductance with dilution, especially near infinite dilution. The increase in molar conductance with dilution is due to increase in number of ions. Thus, the increase in molar conductance lambda m with dilution in case of weak electrolyte is due to increase in degree of dissociation or degree of ionization of electrolyte on dilution. However, there is no indication of limiting value of lambda m naught even when the concentration approaches zero. Figure from figure 7 it is observed that curve for strong electrolyte becomes linear at low concentration and hence it can be extrapolated to zero concentration to obtain the value of molar conductance at infinite dilution, it means lambda m naught. But for weak electrolyte, the limiting value of molar conductance lambda m naught cannot be obtained by extrapolation. There is an indirect method for obtaining molar conductance at infinite dilution for weak electrolyte which is based on Coleridge law discussed in section 2nd. Section 2nd, Theories of Electrolytic Dissociation and Ostwald Dilution Law. Arrhenius theory of ionization. Arrhenius studied the conductance of aqueous solution of different electrolytes. He proposed that the conductance of solution was due to the presence of ions. Arrhenius put forward his theory of ionization in 1884. Arrhenius theory of ionization is summarized as follows. First, an electrolyte, when dissolved in water, splits up into charged particle called ion. The positively charged particles are called cations and the negatively charged particles are called anions. In modern view, the theories assume that the electrolytes are already ionized in the solid state and these ions are held by electrostatic force. When the electrolyte is dissolved in water, the electrolyte dissociates to form separate cation and anion. Thus, AB gave rise to A positive plus B negative old form, whereas in modern form, A positive B negative give rise to A positive plus B negative. For this reason, this theory is called as theory of electrolytic dissociation. Second, the charge carried by cation is equals to the charge carried by an ion. As a result, the electrolyte solution is called electrically neutral. Third, the charged ion moves through the solution towards the positively charged electrodes. This migration of ions causes the passage electric current through the electrolyte solution. This explains the conductance of electrolyte and the phenomena of electrolysis. Fourth, the electrolyte may not be completely ionized. The ratio of dissociation molecule to the total number of molecule is called the degree of dissociation, denoted by alpha. Thus, degree of dissociation alpha is equals to number of molecule dissociated divided by total number of molecules. Fifth, the ions formed in the solution constantly reunite to form undissociated molecule. Thus, a state of equilibrium exists between the undissociated molecule and the ions formed by the dissociation of electrolyte. AB equilibrium sign A positive, B negative. The equilibrium constant for this equilibrium is written as K is equals to A positive, B negative divided by AB, where K is called the dissociation constant. 6. The degree of dissociation increase on dilution and become maximum at infinite dilution. 7. The electrical conductance of an electrolyte solution depends upon the number of ions present in the solution. So, greater the degree of dissociation, higher is the conductance. Thus, the degree of dissociation of an electrolyte determines whether it is a strong electrolyte or weak electrolyte. Mineral acid like H2SO4 HCl, alkalines like NaOH, and salt like NaCl, NaNO3, etc. have high conductance value because they are almost completely dissociate in aqueous solution. These solutions are termed as strong electrolytes, whereas organic acid like CH3C double bond OH, formic acid, some inorganic acids like H2CO3, H3PO4, and bases like NH4OH, MgOH twice, etc. have poor conductance because they have low degree of dissociation. Such substances are termed as weak electrolytes. Factor affecting the degree of dissociation. The degree of dissociation of an electrolyte depend upon the following factors. First, nature of the solute. Some electrolytes like inorganic acid, bases and salt are almost completely ionized in aqueous solution. These are termed as strong electrolytes. Some substances like organic acid and bases dissociate only to a small extent and are called weak electrolytes. Second, nature of the solvent. In solid electrolyte, the ions are held by strong electrostatic force of attraction. Every solvent have a definite value of dielectric constant which is defined as its power to weaken then these force of attraction and cause the dissociation of the electrolyte. Solvents with higher dielectric constant are highly ionizing while those have low dielectric constant are poorly ionizing. For example, water has a very high dielectric constant equal to 80. The ionic compound get quickly dissociate in water as compared to other solvent. Third, concentration. The degree of dissociation of an electrolyte increases as the concentration decreases. As the concentration approaches zero and dilution approaches infinity, the degree of dissociation approaches unity, it means its limiting value. Fourth, presence of common ion. The degree of dissociation of an electrolyte is suppressed in the presence of an electrolyte that furnishes a common ion. This effect is termed as common ion effect. For example, the dissociation of H2S decrease in the presence of HCl. Fifth, temperature. The degree of dissociation increase with the rise in temperature. Ostwald dilution law, ionization of weak electrolyte. It has been mentioned earlier that weak electrolyte are ionized only partial. According to Arrhenius' theory of ionization of ions formed as a result of dissociation of weak electrolyte are present in dynamic equilibrium with the undissociate molecule. Consider the ionization of a binary weak electrolyte. AB equilibrium give rise to A positive plus B negative. In 1988, Ostwald applied law of chemical equilibrium to such chemical equilibria and obtained a relationship called Ostwald dilution law. Let C moles per liter be the concentration of electrolyte in the solution and alpha be its degree of dissociation. The concentration of various species at equilibrium would be as under. AB aqueous give rise to A positive aqueous plus B negative aqueous. Ionic initial concentration of AB is C and A positive and B negative is 0 and 0. Equilibrium concentration of AB is C minus C alpha, of A positive is C alpha and B negative is C alpha. Applying law of chemical equilibrium, Kd is equals to a positive B negative divided by AB is equals to C alpha into C alpha divided by C 1 minus alpha is equals to C square alpha square divided by C 1 minus alpha, or Kd is equals to C alpha square divided by 1 minus alpha. First, when Kd is the dissociation constant of electrolyte AB, like any other equilibrium constant, Kd is constant only at constant temperature. For weak electrolyte at ordinary condition, alpha is less 1. Therefore, alpha can be neglected in comparison to 1 in denominators of expression first. Then the simplified formula becomes Kd is equals to C alpha square. Alpha square is equals to Kd by C. So alpha is equals to root of Kd by C. Second, expression first and second are the forms of Ostwald dilution law. Expression second can be expressed as alpha is directly proportional to 1 by under the root of C. From equation second, it is obtained that the degree of dissociation alpha increase as concentration decrease. As concentration approaches 0, alpha approaches 1. Thus, Ostwald dilution law may be stated as for a weak binary electrolyte, the degree of dissociation is inversely proportional to the square root of the molar concentration. Further, as C is the concentration in mole per liter, then the volume V of solution containing 1 mole of electrolyte will be 1 divided by C liters. It means V is equals to 1 by C. Equation first and second can be written as Kd is equals to alpha square divided by 1 minus alpha into V, and alpha is equals to root of Kd V, where V is the volume of solution in liters containing 1 mole of the solute. Thus, Ostwald dilution law may be state as for a weak binary electrolyte, the degree of dissociation is directly proportional to square root of the volume in liter containing 1 mole of the electrolyte. Validity of Ostwald dilution law. The test The reliability of Ostwald dilution law equation first and second, the degree of dissociation alpha is determined from conductance measurement at various concentration for different electrolyte. The value of alpha are obtained experimentally using the following expression: alpha is equals to lambda c divided by lambda naught, where lambda c and lambda naught are the equivalent conductance at concentration c and infinite dilution respectively. These values are determined from conductance expression using Coleridge law. The value of alpha are then substituted in expression Kd is equals to alpha square divided by 1 minus alpha v. If the value of Kd are found to be constant, the Ostwald law is verified. Limitation of Ostwald dilution law. Its limitations are explained as follows. First, Ostwald dilution law hold good only for weak electrolyte in dilute solution and fails completely in case of strong electrolyte like HCl, NaOH and salt, etc. Second, the Ostwald law is based on Arrhenius theory of dissociation, according to which only a fraction of electrolyte dissociate at ordinary concentration and complete dissociation occur only at infinite dilution. This is true only for weak electrolyte, as strong electrolyte are almost completely dissociate at all concentration. Hence, the formula lambda c divided by lambda naught does not give correct value of alpha. The derivation of Ostwald law is based on the law of mass action, which is not applicable to the ionic equilibrium where the concentration of ions is high in case of strong electrolyte. Thus, the law of mass action in the simple form does not hold good for equilibria involving strong electrolyte. As a result, the correct value of alpha is not obtained, hence Ostwald law is not obeyed in case of strong electrolyte. Explanation for failure of Ostwald dilution law. The failure of Ostwald dilution law in case of strong electrolyte has been satisfactorily explained by Debye and Huckel 1923 and Onsager 1927 according to them. First, strong electrolyte are almost completely dissociate at all concentration. It means alpha is equals to 1. Second, the ratio alpha C divided by alpha naught does not represent the degree of dissociation alpha of strong electrolyte, but it is only a conductivity ratio. For strong electrolyte, alpha is equals to alpha C divided by alpha naught does not hold because when alpha is equals to 1 for strong electrolyte, alpha C is not equals to alpha C divided by alpha naught. Third, in case of strong electrolyte, the increase in alpha CV dilution is not due to the increase in degree of dissociation as alpha cannot exceed unity, but due to the increase in mobilities of the ion of strong electrolyte. Fourth, the lower value of alpha C as compared to value of lambda naught is due to the decrease in mobility of the ion arising from relaxation and extrophoretic effect. However, at infinite dilution, these two retarding effects disappear, hence the value of lambda c become maximum at infinite dilution, it means lambda naught. The result obtained for weak electrolyte, namely acetic acid, and for strong electrolyte, namely KCl, are given in table 3. It is clear that for acetic acid, the value of Kd remain constant for dilute solution, whereas for KCl, the value of Kd fails rapidly with dilution. Application of Ostwald dilution law. Ostwald dilution law is applicable only for weak electrolyte. It is used in calculating the dissociation constant Kd of weak acid and weak bases by determining the dissociation alpha from conductance measurement alpha C divided by alpha naught at given concentration. C. Using the calculated value of Kd for weak acid or weak base which is constant at particular temperature, the degree of dissociation alpha of that weak electrolyte can be determined at any concentration C. Limitation of Arrhenius theory. Although Arrhenius theory could successfully explain the behavior of weak electrolyte, yet it could not explain various observed facts about strong electrolytes. Some of the important limitations of these theories are as follows. First, according to Arrhenius theory, ionization of electrolyte take place in aqueous solution. However, Braggs in 1912 through X-ray diffraction study shows that many electrolytes are ionized even in crystalline state. Example: Na positive, Cl negative. Second, Strong electrolyte, NaOH, KCl, etc., conduct electricity even in molten state. So the ionization of electrolyte take place even in the absence of water. Thus, Arrhenius theory could not explain the role in the water in dissociation of electrolyte. Third, Ostwald dilution law, which is based on Arrhenius theory, fails for strong electrolyte. The value of equilibrium constant for dissociation of strong electrolyte using Ostwald law were found to be vary with the concentration of electrolyte. It means a constant value of dissociation constant Kd is not obtained. Fourth, this is good agreement between the degree of dissociation alpha calculated from the conductivity measurement. It means alpha is equals to lambda divided by lambda naught, and the one calculated from measurement of colligative property only for univalent electrolyte like NaCl, etc. But marked disagreement in the value of alpha was found for bivalent electrolytes such as CuSO4, HgSO4, etc. Fifth, Arrhenius theory proposed that equivalent conductance of electrolyte increase with dilution. The increase in case of weak electrolyte is because on dilution more of the dissociate molecule of weak electrolyte dissociate. In case of strong electrolyte like NaCl, which are fully dissociated even in solid state, the increase of equivalent conductance with dilution could not be explained. The increase of equivalent conductance with dilution must be due to some interionic force of attraction between the ions which have not been taken into account by Arrhenius theory. Sixth, it could not explain the variation of transport number with concentration. Debye-Huckel theory of strong electrolyte. In case of weak electrolyte, the increase in equivalent conductance with dilution can easily explain on the basis of Arrhenius theory, according to which the conductance increase due to increase in dissociation of weak electrolyte with dilution. But this explanation cannot be applied to strong electrolyte as they are almost completely dissociate even at moderate concentration. In fact, the concentration of an electrolyte solution depends upon the two factors. It means number of ions in the solution and second, speed of the ion or ionic mobility. In case of weak electrolyte, the increase in conductance on dilution is attributed to increase in number of ions due to increase in dissociation of the electrolyte. The speed of the ions are not affected on dilution because the number of ions formed in case of weak electrolytes is very small, and hence these ions move independent on each other without any interference in their mobility from the surrounding ions. But in case of strong electrolyte, the number of ions formed is very large. As a result, the mobility of the ion is hindered by the surrounding ion. On dilution, the hindrance due to neighboring ions decrease, the ionic mobility increase, and there is increase in the equivalent conductance of strong electrolyte. A quantitative explanation of the behavior of dilute solution of strong electrolyte was put forward by Debye and Huckel in 1923. Their theory is based on the idea that at high concentration the ions are close together. Because of the electrical attraction among the positively charged ion, each ion in the solution is surrounded by a large number of positively charged ions which constitute an ionic atmosphere of opposite charge and hence affect the speed of the ion. The electrostatic attraction among the positively charged ions which offers the speed of an ion in their electric field are known as interionic effect. The two types of interionic effect are described as follows. First, asymmetric or relaxation effect. Consider a central positive ion. This is surrounded by an ionic atmosphere of a negatively charged ion. This ionic atmosphere is symmetrical in the absence of electric field. When an electric field is applied, the positive ions move toward the cathode and the negative ion atmosphere move towards the anode. This leaves a large number of negative ions behind then in front of the positive ion, and then the symmetry of atmosphere above the central positive ion is destroyed. The excess negative ions left behind drag the positive ion backward, and this slows down its motion in the forward direction. This effect arises due to the asymmetry of the ionic atmosphere of an ion and hence is known as asymmetric effect. It can be explained in another way by considering that the positive ions which leaves the ionic atmosphere of negative ion behind has to rebuild a new atmosphere around it. However, the process of building up and dying away of ionic atmosphere is not instantaneous. The formation of new ionic atmosphere does not take place at the same rate at which the old ionic atmosphere dies out. Each of these processes takes some time, which is called the time of relaxation. During the time of relaxation, the old ionic atmosphere drag the moving ion backward and thus retard the motion of the ion. For this reason, asymmetric effect is also known as relaxation effect. Moreover, the central ion moves into an atmosphere where there is an excess of ion and its own charge, and this also have a retarding effect on the movement of ion. Second is electrophoretic effect. In solution, the ions are present in the solvated form. Each ion in the ionic atmosphere is associated with some molecule of solvent. Under the influence of electric field, the central ion moves in one direction and its positively charged ionic atmosphere along with the associative solvent molecule move in that opposite direction. Thus, the ionic atmosphere with its solvent molecule causes a retarding effect on the movement of the central ion. This retarding effect is called the electrophoretic effect. Beside these two effects, another retarding force is the frictional effect offered by the medium due to the viscosity of the solvent and the dielectric constant of the solvent. This frictional resistance increase with increase in the viscosity and dielectric constant of the solvent. Both the factor, it means asymmetric effect and electrophoretic effect, are present in the solution of strong electrolytes and reduce the velocity of the ion in the solution. Hence, the value of equivalent conductance lambda c is lower than the value of infinite dilution lambda naught. D by Huckel-Onsager equation for strong electrolytes. Taking into account these retarding effects, Debye and Huckel 1923 derived an equation to show the variation of equivalent conductance with concentration. Later on, Onsager 1926-27 further extended the theory and derived an equation known as Debye-Huckel-Onsager equation, or simply Onsager equation. For uni-univalent electrolytes, the equation is written in the form lambda c is equals to lambda naught minus bracket 82.4 divided by eta dt की power half plus 8.20 into 10 to power 5 divided by dt की power 3 by 2 lambda naught into root c, where lambda c is equals to equivalent conductance of electrolyte at concentration c, lambda naught equivalent conductance of electrolyte at infinite dilution d, dielectric constant of the solvent, eta is equals to coefficient of viscosity of the solvent t, temperature k of the solution c, concentration of the solution mole per liter. Since the dielectric constant d and the coefficient of viscosity eta are constant for a particular solvent, thus at constant temperature T, the equation first can be written as lambda c is equals to lambda naught minus A plus B lambda naught into root C, where A and B are the constant for given solvent and temperature. The constants A and B involves root dt in the denominator. Thus, when D and T increase, the interionic attraction would decrease. Thus, decrease in equivalent conductance will be less when dielectric constant or temperature is high. The first terms A root C is the measure of decrease of equivalent conductance due to the electrophoretic effect. The constant A in the term involves eta, the viscosity of the solvent in the denominator, showing that in the more viscous solvent, the decrease in equivalent conductance will be less because the speed of both the ions and the interionic atmosphere is slowed down in the more viscous solvent. The second term B lambda naught root C in the equation gives the decrease of equivalent conductance due to asymmetric effect. Verification of Onsager equation. The Onsager equation can be verified by the following test. First, a plot of lambda c versus root c should be a straight line. Second, slope of the line should be equals to a plus b lambda naught. The graph of equivalent conductance lambda c for some univalent electrolytes in their aqueous solution at room temperature 298 Kelvin are shown in figure 9. The dots represent the experimental value and the line represent the theoretical slope. There is a fair agreement between these values for aqueous solution of the uni-univalent electrolyte. The Onsager equation is obeyed at low concentration, but slight deviation are observed at high concentration. Then deviation may due to some retarding force which have been neglected in deriving the equation. From equation 2, it may be observed that the infinite dilution when C is equals to 0, lambda C is equals to lambda naught as expected from this equation. Significance of Debye-Huckel theory. This theory has been used to explain the conductance behavior of strong electrolyte. Debye-Huckel theory successfully explained why the equivalent conductance of strong electrolyte at constant concentration lambda C is less than the limiting value of conductance at infinite lambda naught dilution, in spite of fact that strong electrolyte are completely ionized. We know that electrolyte dissociates in solution to produce cation and anion.